All right, recorded is rolling. It is Monday, October 31st, Halloween days. Okay. We're starting a new week here. I got a starter question for you guys we're about to get to. So one thing at a time. Top scientist. Hey, here's the top scientist for us. Triple the force, gravitation, and orbits. So awesome job if you're on this list. You guys have your quizzes back. I passed back everything so far that you guys turned in, so it's all back in your folders. You guys are going to be back in the lab area later today, so you'll have a chance to get stuff out of your folders. Okay, everything's back there. All right. I know I got a starter question, but you guys got your laptops up. Yeah, thank you for doing that. Pull out your laptops before I hit record. All right, so this link right here, which is also posted to Google Classroom. So over the weekend, if you guys want to go to Google Classroom, just find that. You can just click on the link. You don't have to type in all the characters. Okay. So here's the thing. Our school about a year ago, a few months ago, it signed up for something called NIMSI and MFI. They sent all the AP teachers to this conference in Texas and blah, blah, blah. Right? Anyway, there's this test that as part of this program they want all the AP students to take. Right. So I took it myself over the weekend. Looks that did you guys take the ACT? The ACT? Some of you guys, let me see, show of hands. How many guys take an ACT? Ooh, okay, just a few guys. All right. Well, there's one section called ACT Science. This new test just kind of reminded me of that. It's a lot of graph interpretation. Show of hands. How many guys are in calculus? Calculus. Okay, about half guys. Awesome. I think that subject calculus will help you out on this test. I don't know, maybe I shouldn't give you guys sense, but anyway, of course, it's not going to pick your class grade, but they want you to take a test near the beginning of the year and then take a test near the end of the year, and you're supposed to like show improvement. They're supposed to get metrics on this anyway. Okay. And so anyway, there's a number of graphs. A lot of stuff we've done in this class. If you think about how graphs work, how units work, it'll help you with that particular test. So anyway, that's there. But what are we doing with that? Right. So here's my plan for this week. All right, so there's a bunch of activities I want to do today, including a lab type activity involving Pendulum. You guys remember AP Classroom? That's been open for a good while now. Okay, at some point you guys have to do this. I checked this morning. It looks like about 5 or 6 of you have already done this and turned it in, already submitted it. So awesome if you have. Okay, we're gonna have to cover this at some point. So let's do this by tomorrow. So hopefully you've got at least a start on this so far, and then tomorrow I want to cover these with you guys. Okay, so you guys can have this done by tomorrow. AP Classroom. Right. Always more labs if I can fit those in. I can't. You guys remember doing the projectile lab with those ball launchers with the spring and right? So we're gonna do a very similar setup, but I want you guys to solve for spring constant. And you guys can use conservation of energy to do that. So we'll eventually get there. It's going to be kind of a tight week. I want to fit in all the energy stuff by the end of this week if I can. So college physics chapter 5. I know I assigned you guys a number of problems. Let's see, where's chapter 5? Right, you guys remember this page, right? With this motorcyclist, blah, blah, blah. Right. I assigned you guys, I think like 10 problems from there. All right. I think the way we're going to have to do this is you're gonna have to do the fast version of this where I pull up the solutions and take you guys through my thought process of like what's a good way to set up and solve these problems. Okay. Also, let's bump the homework due date to Monday. So you guys have a few extra days. Of course, I mean, if you knocked out by the end of this week, you won't have to worry about it over the weekend, because I'm also going to give you guys your energy quiz by this weekend, right? So you have that too. Okay. But what I'm thinking is I want to fit in a space and time for you guys to complete the spare test. So if you go to this here, if you at least knock this out today, go to this link and just make an account, right? All right, so that's what I really want you guys to do today. Just make an account. Can you guys make an account today? Right, just username, password, and then blah. Right, so that should take like all of like 2 or 3 minutes. Right, and then when Friday rolls around, what I'll have you guys do is pull up your laptops, and we're going to actually knock this out in class so that you don't have to worry about it at home. That's the alternative. I could just have you guys do it at home. But it's about a 40-45 minute test, right? Which is like perfect for a class period, so we can just knock it out then, right? That's very good. You guys know that Friday's a regular length day, right? It's regular 48-minute classes. Right? We get out of school at 3:30, right? Okay, so we have an action-packed week. Anybody got any questions about anything so far? Okay, and really right now, just the bare link. All I want you guys to do is just create the account and yeah, we'll worry about actually we'll take Friday to not have the class. Right? Everybody good? Okay. Okay. So, well, I don't think have anything else for you guys to do with the laptops at the moment. I mean, if you want them out to like take notes or whatever you want to do with them, that's fine. But I really just want you to make the account right now. Okay. All right. So we've got I think 3 main things to do today. I want to hit the starter question, which is a pretty solid fundamental conservation of energy question. Then I want to knock out some of those. Let's see. I know we're getting real close to the end of this table, so I want to knock out some of those. All right, then set you guys up with this pendulum activity, where you guys get your hands on. You guys remember the speed gates from back in the day? Okay. All right, so first thing here, say you throw a ball straight upwards. You can get the throwing speed. Right? Can you figure out the maximum height? I think I may have asked you this exact question back when we were doing kinematic motion. That might be a hint, a different path through the forest way to solve this. Okay? But you can't solve this conservation of energy. Okay. So does anybody know the answer by this point to that question? If you throw the ball upward at 30 meters per second, how high is the ball going to go? Okay. Of course, I'm rounding gravity field to about 10 meters per second squared. That's implied. We're ignoring air drag. That's also implied. And by this point in the class, you have at least 2 different ways to solve this, right? You can go back to Unit 1, kinematic motion, and pull up those 3 amigos, those equations, okay? Or you could do conservation of energy. And of course, either way you do it, you're going to get the same answer. So anybody figure this out? Give you guys a little more time. Really like somebody to get this one. Sienna got it. Sienna got it. Right. Oh, look, she's one of my top scientists too. Sienna. All right, yeah, 45 meters. 45 meters. How'd you know it was 45 meters? Okay, yeah, that'll do it. Yeah, 900 meters per second squared divided by 20 meters per second squared. Yeah, that's like the last alpha step. Right here, I'll walk you guys through a couple ways to do it that both lead to exactly what Sienna said. The last mouse step is the same regardless. Here's the old way we used to do it. You guys remember these 3 kinematic equations? Let's go way back in the day. Do it the old way. Right now, there's actually multiple options you have within these, but what's the fastest way to do it? Let's see. If I gave you the throwing speed, here, I gave you the throwing speed, right? Okay, so there's one of your kinematic variables. Right? You know gravity field is about 10 meters per second squared. And at this maximum height, what third kinematic value do you know at the maximum height?
Final velocity.
Final velocity, which is what?
0.
0 meters per second, right? Throw it straight upwards. It's gonna be 0 right there. All right, so would you run to this third kinematic equation and say, let's see, I know final velocity is 0. I know this is 30 meters per second. I know gravity pulling down at 10 meters per second squared. Maybe I should call that negative. Okay, they're solving for x, a displacement, in which case this is like maximum height, right? It's like a height guy, right? Right. So, guys, what's 30 squared?
900.
900, right? See, this is 0. Subtract that over 2 times negative 10 is negative 20. What's 900 divided by negative 20? Oh, well, that's what Sienna said to do, right? 900 divided by 20. You get 45 meters. Okay. Now, that's like an old way of thinking about it, though. The new way of thinking about it is you can set up the sum of energy initial equals sum of energy final. This is true for a closed system. Ooh, now if I'm talking about a closed system, here, for completion, let's identify what are the objects in this closed system. I'm thinking of 2. What are the ball and the earth? Baller. There's a baller system. It's a closed system. Okay. This is right after the ball's left your hand. Okay. So what kind of energy at the okay, so thanks. What kind of energy right after the ball's left your hand? It's all kinetic, right? This ball doesn't really have a height or not very much of it, but it's definitely moving. Right? It's on the move. So it's got all this kind of energy. Oh, you guys could have come up with that expression for kinetic energy, right? Right, 1/2 mv squared. Right? You guys know that. We've done plenty of these right, over the last week. Okay? And then when the ball reaches maximum height, oh, dang it, its velocity 0, so it doesn't have any kinetic. Where'd all the energy go? Potential energy. What's the expression for that? MGH, right? Ooh, if you reverse those, that kind of reminds me of the Galileo problem, right? Drops the ball from some height and it lands on the ground with some speed. This is the reverse of that. But either way, it looks like the mass of the ball cancels, which of course it didn't show up in those kinematic equations either. Okay, and now we're not solving for v, which would be square root of 2gh, which is a common thing to do. But instead, we're solving for h. Okay, hey, let's solve in terms of variables. Let's do that because you guys are AP. Okay. Anyway, it's just one step anyway. It's just divide both sides by g. You guys see that? You guys see that the height, and I'll even call this max height, right? Because it's set up to solve for max height, right? You guys see it's going to be the throwing speed squared. I got a 2 down here, and I got a g if you divide the g over. Okay. So now we have a general expression for solving max height based on any throwing speed. Right? You see that? Okay. Let's see what is maximum height specifically for throwing at 30 meters per second. Square that, divide by 2, 10 meters per second squared. Right? Oh, that's 900 divided by 20. Just like Santa was saying, right? 900 divided by 20. All right, we're looking at 45 meters. Boom. So we got 45 meters either way you did. Second. How about this? Right? What if you, here's this follow-up question. What if you tripled the throwing speed? Right? So you throw 3 times as fast. Because if you triple the throwing speed, the ball's going to go how many times as high? 9 times. 9 times the height. Right? You guys see that? Because a factor of 3 on your throwing speed gets squared. It's going to be 9 times the height. Right? You guys see that? Okay. Okay. That sort of reminds me of if you're in a car and you have 3 times the initial speed and you hit the brake, what happens to your braking distance? It's also 9 times the braking distance, isn't it? You guys remember that from last week? Or whenever we did that. Okay, guys do that? Right, any questions? Any questions? Oh, you know what I forgot to mention too is you can step through second by second if you. Oh, so I'm going back to unit 1 again. Okay, if you throw it for 30 meters per second, how fast is it moving right here? Yeah, 20, and then 10, and then 0. Right, so you could like step it off in terms of seconds and say how far would anything fall in 3 seconds? Go to the edge of the cliff, drop the ball. After 3 seconds, it's also fallen 45 meters. Okay, so many different ways to approach that. You always get the same answer. All right, let's knock out this. Let's bring up this table here. All right. So I just referenced this car one. That's a really classic one to know. Right? This cars are. This is an open system example, right? Parts are top 1/2 mv squared. This was 0 joules of energy. The difference is, I should say, the minus force of friction times distance. Maybe stopping distance. It's called, well, I'll call it x. They call it x there. Okay. Maybe I should have written that back in the day when you guys were doing that, right? So this is an open system, right? Start with this kind of energy, subtract this work done by friction, with 0 joules, right? And then the reason I'm emphasizing this again is because we just sort of mentioned this, right? If you like triple the initial speed of the car, you get 9 times the kinetic energy, right? And therefore, you have 9 times the braking distance. Okay. All right. So we're getting pretty close to the end of this thing. Here. Looks like a spring fires the ball vertically to its maximum height. Right. So what's in the closed system? What's one thing? Yeah, the spring. Also the ball and the earth, right? Because there's a height change, so that Earth's gravity is doing some work on the ball too, right? Okay. Oh, now when you push the ball into the spring, it's like spring pressed, spring loaded, ready to go. All the energy is in the lip. Spring. What's the expression for that? 1/2 kx squared, right? And the force it takes to compress it is kx, and the energy stored in it is 1/2 kx squared. Right. So you guys know you have 2 expressions for springs now, right? F equals kx and energy is 1/2 kx squared, right? So you know when to apply those. Okay. By the time the ball gets to point B, has what kind of energy? It's all gravitational potential, isn't it? MGH at point B, right? Ooh, we got spring potential turns into gravitational potential. Okay, wait a minute, isn't the ball in motion between point A and point B? So should I include a kinetic energy term? No, because all I care about is what just at point A and what's just at point B. So I can ignore everything that happens in the middle. Okay, so got that done. So now we can set up an equation. You could solve it. Could you set this equal to this, and you could solve for stuff, right? Like you could solve for, hey, what is H max as a function of like the spring constant, blah blah blah, and the mass of the ball, and so forth, right? You guys could do that, right? Okay. Now, if you would just want to answer this question, what is the speed at point B? Yeah, 0 meters per second. Okay. So maybe not the most interesting question, but they could ask you that. That would be the answer. Okay. They could ask other things like, how about this? What if you compressed it so far, click, right, and then fire? Hey, you guys know those spring cannons that used in projectile motion lab, and we're going to use in a few days again, right? You guys remember they had like 3 clicks, like click, 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 right? So let's say you do the first click, click, right, and then you fire it straight up. It goes to some height. Okay. Now let's go to 3 clicks, click, click, click. So you like triple the compression distance, right? Right. How many times high is it going to go? 9 times. Because the compression also gets squared, right? Okay. What if you brought a different cannon that was 3 times the stiff, and it was the same compression distance, but it was just 3 times the stiff, right? How many times as high? 3 times. Because if that K is factor of 3, get 3 times the energy, it's going to translate to 3 times the height. Ooh, so that's a linear relationship. Okay. So yeah, different ways to deal with that question. Okay. I'll throw one more at you guys. Right. Let's say we've got the same spring cannon and we're going on adventures all around the solar system, like Guardians of the Galaxy, right? All different planets, right? So we're changing planets, right? Okay. And we go to a planet that has 3 times the gravity field of Earth, 3 times the gravity field. Okay. Let's say on Earth, you fire this thing straight up and it goes to 90 centimeters, 90 centimeters. Okay. So on this new planet with 3 times the gravity, what's the new height? Yeah, 1/3 as much. And 1/3 of 90 centimeters is only 30 centimeters. Right? It's not going to go as high because the gravity is stronger. Inverse relationship between the G and the H, given an initial amount of energy. Okay. All right. You guys ready for the next one? Any questions? Okay. Next one. A block falls from some height and squashes the spring. Okay. And notice in parentheses that I included a detail that's going to be important for, well, if you next chapter, actually. It's assume no mechanical energy loss during collision. There's like a whole chapter we're going to do just on collision physics, right? Which involves conservation momentum. We haven't quite hit that yet, but we're getting close, right? So anytime something like falls on a spring, you usually just go ahead and ignore that. Sometimes they say assume a very light spring or approximately massless spring. So that'll help you handle that. So we got the it's essentially like the previous one, just in reverse, isn't it? Right. We still got a spring. I guess a block, I called it. So let's call it block, right? In the Earth, right? Because of height change. Right? So we still have those that play, right? But this time the initial energy is what kind of energy? MGH, yeah. So gravitational potential, right? And if it squashes the spring to some maximum amount, then we're talking about what? Like your 1/2 kx squared, right? Like spring potential, right? So something like that. Right? What would the speed at point B be? Yeah, 0 meters per second if it's like squash it maximally. Okay. Now you could like this table. I'm trying to keep a big picture, like really forest for the trees. Right? But if you want to get more into the weeds, there's more I guess detailed ways you could go with this question. Like, hey, that compression X, that compression X. Do you think that's also included in the H? Like if the X is like 10 centimeters and the height of falling is like 100 centimeters, do you think that the height that's falling also includes the amount that's squashing the spring? Yeah, because gravity's still pulling it down while it's squashing. So, if that was significant proportion, then you have to maybe consider that. Okay. Also, the maximum compression of the spring is not equal to the equilibrium compression. Like if you take a weight and you just rest it on a spring and just like where it goes to equilibrium and just sits there at rest, right? There's like an equilibrium squash, right? But if you lift it and then you drop it from some height and it like maximally compresses it, it's going to compress it even more, right? In fact, I know if you turn this upside down, you like hang it from a spring like this, and it's like here. Let me tell you guys something that's going to come back probably in January, but I'll just give you guys the answer now. Okay, if I start this from rest, like right now, there's no force out, and I drop it. Okay? This is going to overshoot its equilibrium position and then come back and eventually reach an equilibrium point, right? So the maximum stretch amount and the equilibrium stretch amount are two different values. In fact, it's a 2-to-1 ratio, and I can prove that to you guys. I'll probably do that in January, right? But so suppose I drop this and the maximum stretch is like 10 centimeters, and then it oscillates a little bit and eventually comes to rest. The stretch amount at that point would be about 5 centimeters. Okay. So just planting an idea that's going to come back a few months from now. Okay, guys, okay. And then let's set this one. The ball is rolling down the hill without sliding, right? So I'm going to include the ball, the earth. Right? I'm also going to include the surface of the incline. Surface of the incline. Okay. Because no, we're definitely getting to a future topic here. This is rotational dynamics. This is going to be Unit 7 by AP's book, so we're looking forward a little bit. Okay. But if there was no friction on the surface, then it would not roll. It would just be like an air hockey puck, right? That's what it looked like. It would look really weird, but that's what it would do, right? So it only rolls because of friction, but the friction doesn't actually necessarily take energy out of the system. If it says it rolls without sliding, right? So this could still be like a closed system where the energy is still conserved, right? And at point A, it would be all mgha, right? Or if you had L and theta, you could do H equals L times sine theta, right? But at point B, there's actually two types of energy, right? Now, there's translational kinetic energy, your classic 1/2 mv squared, right? But there's also a type of energy that we haven't talked about yet, right? So say plus, now still a mechanical form of energy. Right? So I'll call it 1/2 I omega squared, right? Now, you guys know what omega is compared to V. Isn't omega just V divided by R? I bet this ball has like some radius, right? Okay, but what the heck is that I? Now that I is called rotational inertia, or sometimes called moment of inertia. Hey, do you guys think that a bowling ball, like a solid bowling ball and a hollow basketball would roll differently down this incline, right? That's what that I has something to do with, right? So yeah, this is like a future topic, but we'll worry about that later, right? And don't worry about this box, right? We're going to save this for either December or January, depending how the semester plays out, okay? Right, you guys get that? Right, but you see how you can set the conservation of energy equation. All right, okay, you guys good? Okay. Okay. Now this last one with the asteroid. Okay, there's still some stuff I want to tell you guys about escape speed, but I'm going to postpone that story just because I really want to fit in this lab activity. Make sure you guys have time for this, right? So I'll save the story for when I was going to say that for sometime later this week. I'll tell you guys about yeah, we'll come back to that. All right. So the pendulum lab activity. So I gave you guys a page. So this was on your desk when you guys walked in. Right. So on the back side are a bunch of conceptual questions. My conceptual quiz, I'm going to give them a Kahoot. I'll probably upload it for you guys so you have this too. Right. The Kahoot that we do in my other class. Okay. Conceptual questions about energy conservation. Okay. But on this side, there's two labs set up. Okay. So this one we'll save for looks like Wednesday. I'm going to save for this lab. Or sorry, this one that we're saving for Wednesday. Okay. But today, I'm going to have you guys do, this is not going to be a full extensive lab, the one we're doing today. So don't worry about AP write-up or anything like that. But what I want you guys to do is make some calculations and then make some empirical measurements using the speed gate. And I want you guys to see that it all matches. I ran this myself over the weekend and it worked beautifully. It all worked. Okay. So let's look at this pendulum because this is a really nice classic physics question. What is the speed of the pendulum at the bottom of its swing? Right? And wouldn't the speed be maximized at that point? Right? Like here's the pendulum. Right? Here's the bob. Right? One thing that we're assuming is that all the mass is in the bob and that the string itself is either massless or has negligible mass. Okay? We're going to start this at some angle theta. It's going to gonna like swing down. It's gonna keep going, right? This is just part of the story. It has a huge speed down here. I'll call this V, but it is the maximum speed, isn't it? I might call it V max or something. So I'll just call it V. Is that okay? Okay. And wait, did we solve one like this? Like a guy swinging on a vine or something? Right. Okay. Wait, was this is this in here? Was it? No. Okay, I didn't make it one of those. Oops. Maybe I should have, because this is a nice classic question right here. Okay. But you guys are telling me that this does look familiar, so, okay. Let's see if you guys can figure this out. Hey, can you guys solve in terms of variables? Let's do one step at a time. Can you guys tell me what H is in terms of L and theta? Maybe this is in your notes, or maybe you can figure it out from scratch. Do some geometry. Give you guys a hint. It might help to solve for this first. This whole thing is L. I bet if you do L minus this, that will give you that, right? Is that true? Nice little right triangle going on right there, right? Give you a minute to see who's going to get this. Who's going to solve this one? So you guys are trying to figure out what is H, an expression for H in terms of L and theta. Oh, yeah, what you got, Elijah?
H equals L minus cosine of theta times L.
All right, yeah, that sounds about right. Right. So let me step you guys through, and I'll show you guys how you can get what Elijah got. Okay. So first of all, what's the side here? What's this equal to, Elijah? L times
Cosine of theta times L.
There you go. Yeah, L times cosine theta or cosine of theta times L, right? You can throw some numbers in here, but you guys can hear, right? You guys can think in terms of variables. Right? You guys have seen this many times in this class, right? Okay. Oh, and if this whole thing is L, isn't this just L minus this? So you can call this like L minus L cosine theta, right? Okay. And if you wanted to factor out this L, you could do that too. It'll be a little fancy. Right? So do you guys have an expression for the type change just as a function of L and theta? Right? Because when you guys set those pendulums up, you guys see those ring stands back there. It's probably not super easy to hold the ruler up and try to figure out, well, where is it here to here? These are two different times, right? But it's really easy to measure the length, and it's really easy to pull out a protractor and measure this, right? And then bam, you have an expression where you can solve that. Okay. Now that you guys know the height change, go ahead and set up a conservation of energy. Sum of energy initial equals sum of energy final. Going from this point to this point. Go ahead and do that. Okay. Give you guys a head start. You guys see that? Okay. Did you guys just write mgh equals 1/2 mv squared? You guys just did that? Right. But where the h goes, can't you just substitute this in right here? Where that h goes? This right here. Right there. So could it be like g times L 1 minus cosine theta equals 1/2 v squared? I know it cancels out the mass because the mass cancels out, right? Right. And then 2 steps. Cross multiply by 2, take the square root. Did I tell you we're solving for v, right? Right, we're solving for v. Okay. So times 2 square root. Right? So the speed at the bottom of this thing is going to be here. Let's go through the last step right here. Okay. It's going to be a square root. I had to have multiplied the 2 over. I've got a g, and then L 1 minus cosine theta. Hey, remember when Galileo was dropping the ball at the Leaning Tower, and the speed that the ball was hitting the ground was always square root 2gh? That's what this is. Speed is square root 2gh. It doesn't matter, it's a pendulum type shape, right? But we have a special kind of h. It's like a fancy looking h. It's this expression, L times 1 minus cosine theta. But it's the same thing. You guys see that? Right, same thing. All right. So brings us back over to this page. Can you guys write that right here? V equals square root of 2g L 1 minus cosine theta. Big old square root going on right there. You guys just write that right there. Right. All right. So what I want you guys to do is, we got about what 16 minutes. That's perfect. That's perfect. Right. So set up a few pendulums. Now here, try it. See if you can fit in 3 for the end of class. Right. Now you guys know what G is going to be. You guys want to use meters or centimeters today? What do you guys feel like? Meters? Meters? Okay, I'm here more meters. So let's do meters per second squared. Let's use a precise value too. Let's go 9.8 because we're gonna get some measurements. I want to see how close this actually is. Okay, no, doing like a pretty close to around. No, let's do 9.8 meters per second squared. Okay, so that means you're gonna measure the length specifically in meters, not centimeters, right? So, for example, if your pendulum is 60 centimeters long, are you gonna write 60? No, you're gonna write what? 0.60, right? Wouldn't 0.60 be 60 centimeters, which is just over half a meter, right? Which you might have that as one of your pendulum lengths. Okay. Theta. Let's go ahead and do degrees because your calculators are as long as your calculators are programmed in degrees, but also your measuring tool. To have a you guys know what protractor. Oh, here it is. These are all in degrees, so let's just go ahead and do degrees. Okay. Right, so you might be like 30 degrees or 44 degrees, right? Okay, so we're going to do two perspectives on V, which is speed. It's the speed at the bottom. I'm talking about this V right here, this V max, the speed at the bottom. Okay. One perspective is going to be to calculate it. Right? That's why I say calculating. Okay. You can do that expression and bam, you should get like a theoretical value, right? Like a textbook value, right? Okay. Then I want you guys to get an empirical measurement. And the way you're going to do this is you're going to take this. You guys remember how to turn this on? Just hit start. It says 0. Right. Okay. Turn this upside down. Okay. Pull this pendulum back to some angle. Okay. Measure the angle, of course. You know L and theta because you've measured each of those. Okay. Then you let it swing. Swing through. And then it will tell you how fast it's going in meters per second. It says meters per second. Okay. All right. You guys good? Okay. And I bet that these two numbers are going to be extremely close to each other. Because again, I did this myself and it worked out over the weekend. Okay. All right. You guys got that? All right. So you guys got the rest of class to do this. Let me give you guys a checklist here. Right. Hold on to this paper because we're going to use the same page on Wednesday for this. Right. And did you guys also have a chance to go to this link and just make an account today? Right. And then on Friday, I'll have you guys pull out your laptops and we'll actually do this testing class on Friday. Right. Okay, who's got any question? Any question? All right. So you guys got the rest of the class to get a few trials here and see if this works out. Right. And then AP classroom by tomorrow. You guys know tomorrow we're going to cover AP classroom, right? You guys write in your planners, AP classroom. Right. Some of you guys already turned it in. All right, I'll be walking around, help you guys out. Halloween.